In this lesson, we look at various cable approaches used to hardwire network devices, including coax cable, fiber, 10-base N cables, twisted pair, and plenum cabling. You can download the script for this video from above or at the end of the video. Each cable type we look at in this video have characteristics that IT considers when selecting the most appropriate type needed for one or more network connections. One type is not always appropriate for all connected devices across an enterprise. Characteristics include signal distance supported, impact of temperature extremes, possible equipment electromagnetic interference or EMI, regulatory requirements such as the need for plenum cabling, attacks against cables. An example of cable attacks is the LANTENA attack described in the article with the link shown, and bandwidth supported. Coaxial cable, commonly known as coax, was once very popular. It was commonly used in the 1970s, 1980s, and into the 1990s. It quickly fell from use for most LAN implementations as twisted pair cabling became popular. We cover twisted pair later in this video. Coax cables generally consist of 4 layers. The inner conductor is a solid copper wire over which signals are sent. This is surrounded by an insulator. The insulator is then surrounded by a braided metallic shield that helps prevent leakage of signal outside the cable and protects the conductor wire from external interference. The metallic shield is also used to enable two-way communication, one path over the inner conductor and another over the metallic shield. Before addressing broadband and baseband cabling, we need to look at the related naming convention. An example is 100 base T, which follows the pattern NN AAAA ZZ. The two ends represent the maximum speed supported by our cable. In our example, the speed shown is 100 megabits per second. The A's indicate whether it is baseband or broadband cable. The Z's represent the distance signals can travel over the cable or the technology used to make the cable. In our example, the T represents unshielded twisted pair. Most cables used are baseband, as when connecting Ethernet networks. Broadband is usually used over coax cables, such as those used to connect to cable providers. The table shown is based on the current CISSP Common Body of Knowledge. It shows characteristics of various types of commonly found cable types. As you can see, each type of cable has characteristics that an organization needs to consider. To clarify, EMI susceptibility in the 5th column applies to interference caused by electromagnetic fields created by things like electrical manufacturing equipment and electrical wiring components. Twisted pair cabling is usually the preferred option when fiber isn't used. These cables consist of 4 pairs of copper wires, with each pair twisted together. The top left graphic shows unshielded twisted pair, and the bottom right graphic shows shielded twisted pair. Shielded twisted pair cable helps reduce or eliminate EMI by including a foil wrapper around the twisted copper wire pairs. The wires are twisted to help reduce crosstalk between the wires and external radio frequency and EMI interference. There are different types of twisted pair cable, and the correct type must be selected for the network protocols used. This table shows the various categories of unshielded twisted pair cable. The table is based on information contained in a Geeks for Geeks article. The article also includes good information about other cable types, and it can be accessed at the link shown. There are disadvantages when using twisted pair, including cable lengths are usually limited to 100 meters. If a device is more than 100 meters from a switch, router, or other signal-enhancing device, a repeater is needed. Unshielded twisted pair is not a good choice in environments with significant EMI, such as manufacturing environments. We use copper or fiber optic cabling in today's networks. We use copper because it is one of the best materials for conducting signals. The signals are the movement of electrical signals, or electrons, down a wire. Gold is better, but copper is much cheaper. As a signal travels over copper wire, it degrades. This is why there are distance limitations as shown in our previous slide. Copper wire is also susceptible to EMI. Fiber optic cable increases the cost of cabling, but it provides for signal strength that lasts over kilometers instead of meters. It is also completely resistant to EMI. Instead of electrical signals, light pulses are sent through fiber cables. Graphic A shows the construction of a single conductor fiber cable, and graphic B shows a fiber cable with multiple conductors. An example of regulatory requirements for cabling is plenum cabling. Regular PVC used in standard cabling releases toxic fumes when it burns. Using PVC cabling in air handling spaces is a violation of fire or other codes. Examples of air handling spaces include spaces above suspended ceilings, assuming that air is not moved through that area via dedicated air ducts, and the area beneath the floating floor. In this example, plenum cable is used in the drop ceiling space and beneath the raised floor. The in-wall vertical runs are not plenum because they are not in air movement spaces. Plenum cable is composed of fire retardant plastics that will not poison people attempting to vacate a building during a fire. We have looked at distance limitations across various cable types. We have also discussed the need for repeaters when distance limitations are exceeded. However, there are restrictions to how we extend cable. A repeater receives a signal from one cable and replaces it at full strength on a second cable. A concentrator also does this, but it has more than 2 ports. A hub is often used as a repeater or a concentrator. If a set of network segments is created only with repeaters and concentrators, or if multiple repeaters or concentrators are needed for reaching devices that are far from the main network, there are restrictions that should be considered. The 5-4-3 rule helps implement effective use of repeaters and concentrators by specifying 3 guidelines. First, there can be a maximum of 5 segments created with repeaters or concentrators. The segments can be connected by a maximum of 4 repeaters and concentrators, and finally, only 3 of the 5 segments can have user devices or servers or other network devices connected to them. The 5-4-3 rule does not apply to networks using switches, bridges, or routers. The rule was created to provide guidelines for networks using a centralized cable, or trunk, to which device is attached by tapping into the trunk. I have not seen a network configuration like this for many years, but it's important to understand the limitations of repeater use. Well, that's it for this lesson. If you have questions, please ask. And until next time, be careful what you click.